Okay, so I want you to picture the analytics dashboard of this really small local online store.
Right, it's a totally unremarkable Tuesday morning for them.
Exactly. And this particular shop, they sell these custom machined metal puzzles. So very niche market. They usually hover around, I don't know, maybe 20 to 30 concurrent users on their site at any given time.
So the needle on their server traffic gauge is practically just resting on the baseline.
Yeah. Totally flat, just a quiet morning in e-commerce. Nothing out of the ordinary at all. Until exactly 10:14 a.m.
Okay, what happens at 10:14?
At 10:14, a massive social media influencer, like someone with 10 million followers, posts a video of themselves solving one of these metal puzzles, and the link to the store is right there in the description.
Oh, wow.
Yeah. So in less than 60 seconds, that server traffic gauge doesn't just spike, it completely shatters. I mean, they go from 30 users to 30,000 users.
In a minute.
In 1 minute, and then it hits 50,000. It is just this unprecedented tidal wave of digital traffic hitting their infrastructure all at once.
I mean, if I'm looking at that dashboard without knowing about the influencer video, my immediate assumption is that we're looking at an incident report.
Right, because 30 users to 50,000 in 60 seconds?
Yeah, I'm assuming a devastating distributed denial of service attack, like a DDoS meant to just completely overwhelm their bandwidth and take the company offline.
See, that is exactly where my mind goes to. Any seasoned engineer would look at those numbers and assume a fatal server meltdown. The database should lock up. The web server should crash.
They should just be throwing 503 errors left and right.
Exactly. But, okay, here is the twist. The site didn't crash.
Really?
It didn't even slow down. The checkout process remained perfectly fluid. They captured every single sale. And the most baffling part, by the next day, when the viral traffic died down, their entire server infrastructure had shrunk right back down to its normal size.
Huh. Well, that is the real mystery here, because you can't just manifest hardware out of thin air. You can't absorb a 50,000 user spike on a small business infrastructure without a crash. And you certainly can't, drive out to a distributor, buy 100 physical servers, rack them, cable them, and install operating systems in 60 seconds.
Wait, so if that's true, doesn't that mean they had to be using infrastructure that was already built and waiting for them?
It absolutely does. And before we pull the thread on how they actually pulled this off, let me just pause and welcome you to Analyst Mindset. This is a space dedicated to making cybersecurity, networking, and digital infrastructure simple, practical, and easy to understand for everyone.
Yeah, it's so much better to look at real mysteries like this than just, reading a textbook.
Exactly. If you enjoy learning by thinking like an analyst instead of simply memorizing facts, you'll probably enjoy the conversations we have here. Looking at the evidence of real scenarios like this is how these concepts actually stick.
So our mission for this deep dive is to investigate exactly how that small online store survived the spike.
Right. And to do that, we need to map out the foundational architecture of cloud computing, specifically looking at the core concepts tested in the Microsoft AZ-900 exam and uncover the operational reality of what the cloud actually is.
Okay, so let's look at the scene of the crime. Because something feels a little suspicious here when people talk about this.
What do you mean?
Well, I hear people, especially in the media, throwing around the cloud and the internet like they are the exact same thing. But if we are talking about physical hardware absorbing a traffic spike, the internet itself doesn't process web checkouts.
No, it doesn't. And you're touching on one of the most persistent misconceptions in tech. The internet and the cloud are absolutely not the same thing.
Okay.
The internet is simply the delivery mechanism. It's the global network of fiber optic cables, routers, and cell towers that transmits data from point A to point B.
So the internet is just the transit layer, which means the cloud has to be the actual destination.
Exactly. It's not some invisible fog. It's a physical place. When we say this puzzle store was operating in the cloud, we mean their digital operations were running inside massive, highly secure, physical data centers. In this case, data centers owned and engineered by Microsoft.
So we are talking about, huge warehouses.
Oh, facilities the size of multiple football fields. They are packed row after row with racks of high-density servers powered by redundant substations and cooled by massive industrial systems.
Wow.
Yeah, that physical hardware is the cloud. Providers like Microsoft Azure, AWS, and Google Cloud allow you to access the compute power of those physical machines over the internet.
Okay, but am I missing something here? If the store is using Microsoft's physical hardware, they aren't getting a whole physical server dedicated just to them, right?
Yeah.
I mean, a tiny puzzle shop doesn't need an entire rack of enterprise hardware.
Right, and that is where the concept of virtualization comes in. You don't rent the physical metal box itself, you rent a virtual machine, or a VM.
A virtual machine. Okay.
Yeah, a piece of software called a hypervisor sits on the physical server and carves its massive pool of CPU and RAM into smaller, isolated virtual computers. So that puzzle store might be running their web server on a virtual machine that only uses, say, 2% of the underlying physical server's capacity.
Okay, I think I see a pattern here. Here is how I'm connecting these clues. The store didn't have to scramble to buy hardware during that 10:14 a.m. traffic spike because Microsoft operates as this massive pre-provisioned hardware reservoir.
Yes,
The physical servers were already racked, powered on, and just waiting.
that is the operational reality. But let's look at the motive. We know where the servers actually live. But why would a business structure their entire operation this way?
Well, historically, they didn't, right?
Right. For decades, the standard was to buy your own servers. You built a server room, you hired the IT staff, you maintained the blinking lights. Why did the entire tech industry shift away from that?
To understand the motive, we have to look at the financial architecture, don't we? Like capital expenditure versus operational expenditure, or CapEx versus OpEx.
Yes. Walk me through how you think that applies to our puzzle shop.
Okay, well, buying your own physical servers is a capital expenditure. It is a massive upfront sunk cost. But it's worse than just the initial price tag. Let's use a logistics analogy. Imagine your business needs to ship products across the country. Buying your own servers is like deciding to buy your own dedicated freight train.
Okay, I like this.
You have to buy the locomotive, lay the tracks, hire the engineers, and pay for the fuel and maintenance.
And you have to size that freight train for your absolute maximum capacity.
Yeah.
If you know you're going to get slammed with orders on Black Friday, you have to buy a train with 50 boxcars.
Exactly. But what happens on a random Tuesday in March? You only need one boxcar to ship your daily orders, but you still own, maintain, and pay for all 50.
Right.
The other 49 boxcars are just sitting there burning money, waiting for Black Friday. That is the traditional on-premises server model. You are paying for peak capacity 365 days a year, even when you aren't using it.
So moving to the cloud shifts that CapEx model into an OpEx model, operational expenditure.
Right. Moving to the cloud is like deciding to stop owning trains and just ship everything via FedEx.
Yeah, perfect.
You don't care how many planes or trucks FedEx owns. You don't care about their maintenance schedules. You just hand them your boxes, and you only pay for the exact weight and distance of the packages you actually ship today.
You're completely outsourcing the infrastructure management. The puzzle store rents the virtual machines and databases from Microsoft, completely eliminating the need to be server mechanics.
Which is a huge relief for a small business.
Huge. They don't worry about hardware depreciation, cooling costs, or replacing a failed hard drive at 2 in the morning. Microsoft handles the physical layer, the store handles their business.
It makes total financial sense.
Right.
But this still leaves our central mystery completely unresolved.
The 10:14 a.m. influencer spike.
Yes. Because the CapEx versus OpEx shift explains why they didn't want to buy hardware upfront. It explains where the servers were, but it does not explain the physics of how they survived the impact.
Right, because if you overwhelm FedEx,
Exactly. If you use FedEx to ship 10 boxes a day, and suddenly you show up with 50,000 boxes with zero warning, the local FedEx branch is still going to bottleneck. So how did the store's rented virtual machines not completely melt down under all that sudden weight?
to solve that, we have to examine the actual mechanics of the cloud. The key piece of evidence here is a concept called elasticity, which is achieved through auto-scaling and load balancing.
Auto-scaling. So, meaning the system detects the load and scales the resources automatically.
Yes, it's entirely data-driven. The cloud provider constantly monitors the health and performance of your virtual machines. This is called telemetry.
Telemetry.
The system is watching metrics like CPU utilization, memory usage, and network traffic in real time.
Okay, let me think through this timeline then. At 10:13 a.m., the store has one virtual machine handling the website. 30 users are browsing. The telemetry shows the CPU is sitting at maybe 10%. Everything is totally calm.
Then 10:14 a.m. hits. The influencer posts the video, traffic starts flooding in, thousands of HTTP requests start hammering that single web server.
The CPU usage on that VM spikes. It goes from 10% to 50% to 80% in seconds. On a traditional on-premises physical server, it hits 100%. The requests queue up, the server crashes, and your customers get a page timeout. Game over.
But in a cloud architecture, The engineers configure an auto-scaling group with specific triggers.
What kind of triggers?
They write a rule that says, if the average CPU utilization of my web servers exceeds 75% for more than 1 minute, automatically provision and deploy a new virtual machine.
Oh, wow. So before the first server can crash, the cloud platform's automation kicks in. It takes an exact clone of the web server and spins it up on Microsoft's available hardware. Now they have 2 servers.
Exactly. But the traffic keeps coming. 50,000 users are pouring in. So the CPU on both servers hits 80%.
And the trigger fires again.
Yep. It spins up a third, a fourth, a tenth, a 50th VM. Because Microsoft's hardware reservoir is virtually limitless from the perspective of a small business, the environment just keeps horizontally expanding, scaling out to meet the exact demand of the traffic wave.
I'm following the scaling, but wait, if that's true, doesn't that create a massive traffic jam at the front door?
What do you mean?
Like, if I'm user number 40,000 clicking the link, how does my browser know to go to newly created virtual machine number 42 instead of the original server that's already choking?
That is the crucial missing link. You can't just add servers and expect the traffic to figure it out. You have to introduce a load balancer.
A load balancer. It sounds like a digital traffic cop.
That is exactly what it is. The public IP address that the influencer linked to doesn't point directly to a single web server. It points to the load balancer.
Oh, I see.
As those 50,000 users hit the link, the load balancer stands at the front gate, looks at the incoming requests, and distributes them across the available pool of servers.
So it's actively managing the flow. It sends user A to server 1, user B to server 2, and so on.
Yes, and as the auto-scaling group spins up new servers, they register themselves with the load balancer. The traffic cop sees the new lanes open up and instantly starts routing traffic to them.
That's incredible.
Furthermore, it performs constant health checks. If server number 12 gets bogged down or fails, the load balancer simply stops sending traffic to it and reroutes users to healthy servers.
That is just brilliantly elegant. The auto-scaling group provides the muscle, and the load balancer provides the logistics. That entirely solves the operational mystery of the 10.14 a.m. spike.
It does.
They survived because their infrastructure was elastic. It stretched out automatically, distributing the massive wave of traffic across dozens of temporary servers without human intervention.
And what happened the next day?
Well, the next day, the viral wave ended, right? The 50,000 users dropped back down to 30. So the telemetry saw the CPU usage across those 50 servers drop to like 1%.
And the auto-scaling triggers work in reverse, too.
Right. So there's a rule that says if CPU drops below 20%, terminate the extra servers. It scales back in. The infrastructure systematically deletes the temporary virtual machines, shrinking the environment right back down to that single original server.
You've nailed the architecture. They borrowed an army of compute power for 24 hours and then vanished it.
Okay, but let's look at the fallout of that event. If you are instantly creating and destroying dozens of enterprise-grade servers, how does the billing actually work?
I was wondering when you'd get to that.
Because wouldn't that be a total nightmare to invoice? If I am constantly spinning up resources for 3 hours and 12 minutes and then deleting them, how do you manage that from a procurement standpoint?
This is where we bring in the final foundational concept of cloud computing, the pay-as-you-go pricing model.
Oh, okay. We mentioned OpEx earlier, the operational expense. This must be the mechanism for it.
Precisely. Think about how you pay for electricity at your house. You don't sign a contract to pay a massive flat fee to fund the entire city's power plant.
No, I just pay my bill.
Right, you have a meter on the side of your house. When you turn on your air conditioning, the meter spins faster, and you pay for what you pull from the grid. When you go on vacation and turn everything off, the meter practically stops, and you pay almost nothing.
The utility model. You only pay for exactly what you consume. So in the cloud, you are billed for compute time.
We are talking down to the minute, or even the second, depending on the service. When our puzzle store was running normally with 30 users on a single VM, their digital meter was barely moving. They were paying pennies an hour.
And when the influencer hit and the auto-scaling group spun up 50 servers,
the meter spun wildly. For that specific 24-hour period, they were being billed for the combined compute time of 50 servers. They paid a much higher enterprise-level rate for that single day.
But the second those servers were automatically deleted, the billing stopped. That completely flips the script on how businesses handle financial risk. I mean, in the old CapEx model, if you wanted to prepare for a viral spike, You had to gamble hundreds of thousands of dollars on physical hardware that would just sit idle most of the year.
Yep.
In the cloud, the puzzle shop didn't have to risk a dime in advance. They just paid a slightly higher utility bill for the exact 24 hours they were actually processing the thousands of extra sales.
Which is exactly why the AZ900 exam heavily emphasizes the economic benefits of the cloud, not just the technical ones. This utility-style, highly elastic model is the industry standard.
It makes sense.
Whether you are using Microsoft Azure, Amazon Web Services, or Google Cloud Platform, the fundamental mechanics remain the same. Virtualized resources, load balancers, auto-scaling groups, and pay-as-you-go billing.
Okay, let me summarize our findings to make sure we've captured the full picture of this case file. We started with the mystery of a tiny online store surviving a massive digital tsunami without buying any hardware.
And we broke down the mechanics of how they pulled it off.
Right. We uncovered that the cloud is not magic. It's a vast reservoir of physical hardware located in massive data centers accessed over the internet. Businesses use this through virtualization, renting virtual machines to completely avoid the massive capex costs of buying and maintaining their own physical servers.
The shift to FedEx logistics rather than owning the freight train.
Exactly. And most importantly, we solved the physics of the traffic spike. Through telemetry, the infrastructure detected the rising CPU load. The auto-scaling group dynamically spun up extra servers to handle the weight, while the load balancer flawlessly directed the massive crowd of users across the new hardware.
Spot on.
And then the next day, it automatically deleted the unneeded servers, and because of the utility billing model, the business only paid for the exact compute seconds they consumed during the spike.
It is a brilliantly engineered system. It provides high availability, fault tolerance, and massive scalability. It's the reason modern applications can handle global demand.
It is an airtight architecture. But, before we close this file, I'm thinking about a secondary angle here, a new variable.
I was waiting for the other shoe to drop. What are you seeing?
Well, now that we've solved how they scaled, think about the security implications of this entire model. The store is capturing credit card numbers, home addresses, sensitive customer data, and all of that data is sitting on a rented virtual machine inside a massive data center owned by a Microsoft, AWS, or Google.
Yes. The data is physically sitting on someone else's computer.
Wouldn't an attacker try to exploit that exact setup? I mean, if you own your own physical server in a locked room in your office, you control the physical access. You have the key to the padlock.
Right.
But in the cloud, you don't own the building. You don't own the physical server. The hard drive your customer data is sitting on right now might literally be shared with another company's virtual machine.
You're touching on the most critical vulnerability in the entire paradigm.
Because if you don't own the physical hardware, how do you actually lock the door? How do you keep the other tenants out of your data when you are all sharing the same physical warehouse? You have to trust the landlord. How far does that trust actually go?
That is the single most important question in cloud architecture. And the answer involves a highly complex framework known as the shared responsibility model.
The shared responsibility model.
Yeah, it dictates exactly where the landlord's security stops and where yours begins. But investigating where that line is drawn is a complex enough mystery for our next case file.
I am already looking forward to digging into that one. We solved the operational scaling mystery, but in doing so, we just uncovered a massive fundamental security challenge.
That is the reality of the work.
Sure.
Every investigation inevitably uncovers another layer of the story. If you enjoy exploring cybersecurity this way, critically analyzing the architecture instead of just memorizing the terms, we'd be glad to have you join us for the next one.
Definitely.
Until then, keep questioning what you see on the dashboard.